Okay,
Yeah.
thanks for joining us for the third installment of Matthijs Va. And I'm not going to introduce him a third time, so go ahead, Matthijs.
Thanks, Awad. Okay, so welcome to this third part of the tutorial about mathematical foundations of automatic differentiation. We've been talking mostly about a specific aspect of the mathematics behind automatic differentiation, and namely, it's the aspect that when you formulate it on functional programming languages, automatic differentiation algorithms tend to form a sort of structure-preserving functor. And we were making that precise last time. We got into the point where we define the syntax of the source language, so that's the language that the programs that we want to differentiate come from, as a category. And then we saw that as a target language for automatic differentiation, you tend to want to use a sort of language that has both Cartesian types and linear types, where the linear types represent a sort of notion of commutative monoid, and that is because you, having a sort of zero and addition is very fundamental for the technique of automatic differentiation. And now we got to the point that we saw that the codomain for this functor, if we want to see automatic differentiation as a functor, should be a sort of sigma type of categories, so a sort of sigma type category. Right, so the point was automatic differentiation forward mode was going to be a functor from the source language, which is just a simply typed lambda calculus, to a sort of sigma type category that you formed out of the target language, so the language that the programs that we have differentiated will land in, where we take a sigma type of the linear fragment of the language over the Cartesian fragment. So that sort of means that automatic differentiation is going to produce programs that have both a Cartesian component, which is the computation that calculates just the function values. So in the AD, in the automatic differentiation literature, people call this the primal computation, and then a linear computation that is executed afterwards that sort of propagates the derivatives forwards, so the tangent values forwards in the case of forward AD, or propagates the cotangents in reverse in the case of reverse AD. And this reversal happens because we are taking the opposite category of the linear fragment in before taking the sigma type in the case of reverse AD. So the so the part that I'm going to be talking about now is to analyze the categorical structure of these sigma types of categories, which is very fundamental for understanding what the algorithm will look like, because the whole point is the algorithm is defined as a structure-preserving functor, as the unique structure-preserving functor on the syntax, and we can calculate what that functor looks like if we know what the categorical structure of these sigma types looks like. So we're going to look at what products, exponentials, coproducts, and such look like in these sigma types of categories. Okay, so in many ways, the main mathematical contribution behind this work that I've been doing, that I've been calling CHAD, so combinatory homomorphic automatic differentiation, is this analysis of the categorical structure of sigma types of categories. And a lot of this work is a collaboration with Fernando Lucatelli-Nunes, who's been doing particularly the very complicated math when the categories get more complicated with dependent types and inductive types and that sort of thing. Okay, so we're going to focus in particular on the structure of sigma types of categories where the fiber categories are all enriched over commutative monoids, because that's the case that is interesting for automatic differentiation. Right, and we're going to look at both results for the case of locally indexed categories, so that's the case of the simply typed world, and in the case for general indexed categories, which is the dependently typed world. And generally, we can live in the simply typed world as long as we don't have coproducts in our language. And once we throw coproducts in our language, the dimension of the space of tangent vectors can depend on the base point that we choose, so then we need dependent types. Okay. So I'd like to, before I start with this sigma type category section, I'd like to recall one basic fact about commutative monoid enriched categories, that if you haven't seen it before, maybe you can try to prove it as an exercise. And that is that if you have a category that has finite products and then it is enriched over commutative monoids, if and only if those finite products are biproducts. So if they're also coproducts in a canonical way. And this is a really nice property that we have in our categories, therefore, and we will exploit it a lot. that because our categories are commutative monoid enriched, the finite products are byproducts, so also co-products. Okay, so first of all, what do products look like in sigma types of categories? So in the case of a locally indexed category, so that's the case where all the fiber categories of L have the same objects and the substitution functor is identity and object, they're quite simple. In particular, for the case of the covariant sigma type, we form a product of C1, L1 with C2, L2 just by taking the product in C and taking the product in L, right? And if we dualize the fiber, so if we dualize L, we need to take the product in C and the co-product in L, right? By duality. And therefore you can note that, yeah, in case L is commutative monoid enriched, because we have byproducts, the product and the co-product in L will coincide. And so the product and co-product in the sigma type of L over C and the sigma type of L op over C are going to be the same. Okay, now in the case with dependent types, things are a little bit more complicated. The formulas look slightly more complicated, but the idea is basically the same, right? To take a product of one of these pairs, C1, L1 and C2, L2, where C1 is an object in C and L1 is an object in L of C1. L1 is an object in L of C1, then we just take the product in C and we take the index product in L. So we're assuming that we have products in L that are stable under change of rates. And then we can form products in the sigma type of categories. Yeah, so I'd like to note that in case our category L is commutative monoid enriched, which is going to be in the case of automatic differentiation, these products in the covariant and the contravariant sigma type category are going to be the same because products are byproducts. Okay, so I think this is probably well known, at least among some people. Something that, yeah, one more aspect that's nice about these products is that they're fibered in the sense that they lift the products from C, right? So these sigma types of categories form a fibration over C. And because the first component of this product is just ordinary product in C, it means that we're lifting the product from C to the total space of the fibration, which will have nice consequences. Okay, so now on to exponentials. I don't think this was so well known. So it's a slightly novel construction of exponentials that I gave in this work. That's quite surprising. And what's interesting is that it only works, as far as I can tell, if the fiber categories are enriched over commutative monoids. So the exponentials are a little bit surprising. So bear with me. The exponential of C1 L1 to C2 L2 ends up being a pair of spaces. So the space of primals will have this funny structure that it's built out of the functions from C1 to the product of C2 with the linear functions from L1 to L2. Right, so we're using the exponential in C, we're using the product in C, and we're using a sort of C object of L morphisms to build this first component of the exponential. Okay, and the second component of the exponential is a sort of power of L2 with C1. So we need a sort of power object to build it. So how do you interpret this exponential? Basically, the idea is we think of C1 and C2 as the spaces where the primal values of our functions live, right? And L1 and L2 are going to be the spaces of tangent vectors. So what we're saying is the space of primal values at a function type is going to be a function from primal values at C1 to primal values at C2, together with a linear function that goes from L1 to L2 for each C1. So we're sort of packing both the function and its derivative into the primal associated with the function. And now what's this tangent, or what's this second component? Well, the intuition there is it's a function from the primals of C1 to the tangents at the codomain L2. So what's happening really is we're splitting the derivative of a function into two parts, right? If we have a lambda in a program, we can differentiate it either with respect to the arguments of the lambda, or we can differentiate it with respect to the context variables that we capture, right? If you have a higher order language, a lambda expression can either, it has some arguments that are explicit in the form of function arguments that are bound by the lambda abstraction, and other arguments are implicitly captured from the context. And so the derivative with respect to the function arguments ends up in this first component. So in this primal component, the derivative with respect to the context variables that are captured are in the second component. That's what's going on here. So it's sort of funny. And now we can dualize this, of course. If we dualize L, so we see what the formula should be not for forward AD, but for reverse AD, then all that happens is, well, in the primal component associated with the function type, we swap L1 and L2 because the derivatives are, we're not looking at derivatives, but transpose derivatives, which go backwards. And the power changes into a co-power, right? So how you can think about that co-power is it's a sort of C1-fold co-product of the commutative monoid L2 with itself. And I'll show you in a moment how you can implement that in a functional language, even if the language doesn't have support for linear types. Okay, so again, the first component, so the primals associated with the function type hold not just the computation of function values, but it also holds the transpose derivative computation with respect to the function argument of the lambda that the lambda captures. And then the second component of the cotangents associated with a function will hold the adjoint contributions that need to be propagated back to the context variables that are captured in the lambda abstraction. So that's the basic idea. You get this funny split between function arguments and context variables that are captured. Now, something that is important to note here is these exponentials are sort of weird because they're not fibered, right? They're not fibered over C in the sense that the first component of the exponential is not just the function type from C1 to C2. So we're not just lifting the exponentials from C to the sigma type of categories, but they're different. And in that sense, they're not very well behaved. Okay, again, we can repeat this trick in a world where we have dependent types, so where we have a general commutative monoid enriched index categories. And then, yeah, all function types in C change into dependent function spaces. All products change into dependent products, so sigma types. We keep the ordinary linear function type, and we apply it in each fiber. And then instead of a power and a co-power, we need a dependent power and dependent co-power. And people have studied these. I studied them in my PhD, for example. So this is, yeah, the idea is the same. The formulas just look a bit more complicated. But again, it works for index categories. And after doing this work, we realized that actually there's a relationship with some known work after all. And it turns out that what we've given here, this exponential construction, at least in the special case, was already known to Martin Hyland and probably already to Diller and Nahm, because what we're doing is we're generalizing Martin Hyland's construction of his categorical account of the Diller-Nahm variant of the dialectica interpretation. So I've heard multiple people say AD is related to dialectica in some way. I think this is the precise relationship. These formulas generalize the Diller-Nahm variant specifically of dialectica, which also uses these commutative monoids. Okay, so that's the exponentials. The co-products luckily are a bit simpler. So the co-products are a bit funny in the sense that they only work if we're working with a general index category. They're not going to work in locally indexed categories. So in that sense, we don't really have much of a hope of differentiating languages with some types in a nice way if we don't have dependent types in the target language. But I'll show a way of getting rid of the dependent types in a bit. Okay, so the idea is we demand that we have an extensive indexed category. And what that means is that we want the morphism that goes from the fiber over a coproduct of C1 and C2 to be to form an isomorphism to the product of the fibers over C1 and C2. So what that really means is, in an extensive index category, we can define dependent types out of depending on the coproduct by a case distinction. So we can define types via pattern matching. And this is, for example, true in any proof-assistant or a dependently typed language that has coproducts and a universe of types, right? Because you can just construct the type using a case distinction on the coproduct. So that's important here. We're writing this defining of types via a case distinction here as a sort of co-pairing. What we're saying is the coproduct of C1 and L1 with C2 and L2 is, well, in the first component, we just take the coproducts of the spaces of primal values. And in the second component, we take the case distinction of the spaces of tangents or cotangents. And this gives the coproduct in both the covariant and the contravariant sigma type category. So what this means is you probably already know this from differential geometry. It means that the tangent bundle, the spaces of the tangent spaces, so the spaces of tangent vectors associated with, I guess, a smooth space that has multiple connected components, are just constructed locally. So you just look at the local environment to construct a space of tangent vectors, and you say, well, you construct them through a case distinction by saying, okay, what connected component am I in? And then I only need to look at my current connected component to construct my tangent space where I'm at. Okay. But this construction does not work for any non-trivial locally indexed categories. And it means that to have nice derivatives of languages with some types, we need to have dependent types in our target language. On the other hand, these coproducts are fibered in the sense that the first component is just the ordinary coproduct in C. So we're lifting the coproduct of C to this total space of the fibration of sigma CL and sigma CL up. So that's nice. Okay, the next part I'm going to go over a little bit quickly. Fernando proved this really beautiful result where he showed that we can actually construct initial algebras and terminal coalgebras for fibered endofunctors on these sigma types of categories in a very pretty way. And that means that we have a way of performing automatic differentiation on languages with inductive types and co-inductive types. And it's really very elegant. So what ends up happening is a lot of endofunctors that naturally arise are fibered endofunctors. So that means that they consist of two components, a component on the base space on C itself and a component on the fibers that are compatible in a way. And then to construct the initial algebra of these endofunctors, we just take the initial algebra for the primals. So that's the ordinary initial algebra in, for example, the category of sets or in the Cartesian world. And we also take an initial algebra in the fibers, or in the case that we are dualizing the fibers, we take the terminal coalgebra there. So what this is saying really is that, initial algebras and terminal coalgebras in these sigma types of categories are quite manageable in many cases. And they can just be constructed out of initial algebras and terminal coalgebras in the base space and the fibers. The only thing to take care with is that the initial algebras and terminal coalgebras in the fibers might not be exactly what you're used to, because this fiber category isn't just a Cartesian category, but it's sort of a linear category. So it's not like the category of sets, but it's more like the category of commutative monoids. So you need to think a little bit about what initial algebras and terminal coalgebras look like in the world of commutative monoids. But this gives you a way of doing automatic differentiation on inductive and co-inductive types. That's quite pretty. And that is the reason is that a lot of the functors, in particular any functor that we can build out of constants, products, co-products, initial algebras, and terminal coalgebras, is going to be one of these fibered endofunctors. So we can take their initial algebra and terminal coalgebra, because these initial algebras and terminal coalgebras again are fibered in the sense that the first component is the ordinary initial algebra or terminal coalgebra. So we're lifting the ordinary definitions from the Cartesian world, the world of C, to the world that also has a linear component. So this, sigma type category. Okay, so these are some of the results that we have on the categorical structure of sigma types. We've also worked out how to do iteration and partiality, first order recursion, and we're almost ready to have a nice recipe for higher order recursion as well. So you can really, by analyzing this categorical structure of these sigma types, you can just calculate what the formula should be for automatic differentiation for basically all the language constructs that we've been able to come up with so far. Okay, so I'll show you how that works now. So now we're in a place where we can derive the AD algorithms from their universal property. And let's first do that for just ordinary forward mode AD. The idea is that by the universal property of the source language, we should get a unique structure preserving functor, so a unique homomorphic functor, once we fix the definitions on the generators for the types and for the morphisms. So we need to say what the space of primals and space of tangents associated with n-dimensional real vectors are. Well, we just take the type of n-dimensional real vectors for both the primals and the tangents there. And what do we do with operations? Well, basic operations, we want to use this sort of formula where we say, well, first differentiate the arguments and then apply the operation to the primals and apply some derivative of the operation to the tangents. So what we're assuming is that we need to have a term in our language or a program in our language that correctly implements the derivative of each primitive operation. So for example, if our primitive operation is a sine function, we need to have a cosine in our language, and we would write down the cosine here. Okay, so we need to have, this is important for everything to be correct. And for all the definitions to work, to get started, we already need to have derivatives for all of our primitive operations. And then we get the rest for free. Right, then in particular, we get a type preserving, structure preserving functor on our syntax, such that if two source programs are equal according to the beta-eta equational theory, the programs that are produced are, again, beta-eta equivalent, but we need to add some extra equations for the monoid laws and homomorphism law. But yeah, basically what it means is if the source programs are equal in the obvious equational theory, the programs that this derivative produces are also equal in the obvious equational theory in the target language. Okay, so what we end up getting, the induced definitions that we end up getting from this categorical structure of sigma types is we associate a pair of types with each type. The first component is the type of primal values. The second component is the type of tangents. And we associate with products, just a product in the first component and a product in the second component. And with function types, we associate this funny formula that we talked about before, right? We split up the derivative with respect to the function arguments from the derivative with respect to the context variables. Put one in the primal type and the other one in the type of tangent vectors. So in particular, the type of tangent vector is going to be a linear type. The type of primals is going to be a Cartesian type. And I'm not giving the formulas for co-products here because they introduce type dependency. So the formulas would look a little bit more complicated. Okay, so we can do something similar for reverse AD. You'll notice that it's basically the same as the previous. So we again start with something very similar. The type of primals and cotangents associated with n-dimensional real vectors are just n-dimensional real vectors. That's the obvious definition to start with. And the derivative of a basic operation, again, is achieved by first differentiating all the arguments and then applying the operation to the primal values. And again, we need to have a program in our language already that implements the transpose derivative of all of our primitive operations. And as long as we have that, then we can get started. We have a formula for differentiating the basic operation, and then the category theory does the rest. right? And we get these formulas again that come from the categorical structure of sigma types of these, these contravariant sigma types of categories. So this is these are some of the formulas we get then if we want to differentiate programs. You don't need to understand these or read. And all I want to show is, you get formulas that look pretty standard. It produces code in a lambda calculus with some Cartesian types and linear types. And we'll look next at a way of getting rid of the linearity, such that we can actually implement this as code in a standard functional language. But one thing that's happening that's sort of interesting here is we're again separating. We're seeing here in the rule for function application that we have a part of the derivative that's with respect to the context variables and a part of the derivative that's with respect to the function arguments. And that separation is just what comes from the structure of exponentials in sigma types of categories. So it's sort of forced on us. Now we can do something similar for dual numbers AD. We define it just by sending n-dimensional real vectors to the product of n-dimensional reals with itself. And we do something similar for basic operations. And all we need is a term in our language that implements all the partial derivatives of the operation. And then we get some really, really simple formulas that preserve the beta-eta equational theory, right? So the derivative of a product is just the product of the derivative. Derivative of a coproduct is the coproducts of the derivatives. The derivative of a function type is the function type of the derivative functors. Right, so this dual numbers AD is really much simpler than a non-dual numbers AD. And we can do something similar for reverse mode dual numbers AD. Right, and the formulas are largely the same as for forward mode dual numbers AD. Okay, so these are the how you derive the definitions of AD from category theory. Now I'll say something very brief about how you see that these definitions are correct, or in what sense precisely they are correct. Okay, so we can establish a correctness theorem for these source code transformations in the sense that they, we want to say somehow, or prove somehow that they actually implement derivatives. And it's a little bit tricky how to do that, because we first need to ask ourselves, what does it even mean for these source code transformations to be correct? Because we don't really have an obvious definition of a derivative from calculus that works at co-inductive types or works at function types, right? So the best we can sort of do is say, as long as we have for any program whose inputs are data types and whose outputs are data types, so that means like first order types, it means types that don't have any function types or co-inductive types in them, then the semantics of the syntactic derivative is the semantic derivative of the semantics of the original program. Right? So that's the intuition. Our correctness theorem says that for any of these programs with first order or data input types, so no code data, and data output types, the semantics of the syntactic derivative is the semantic derivative of the semantics of the program. And this is sort of the best we can do. But I would like to note that these programs that the correctness theorem is about might still use co-inductive types or function types internally, right? They're just not part of their interface. They're not part of their inputs or output types. And I think this is the most general notion of correctness I could come up with, because we have a notion of derivative from calculus at data types, but not at co-data types, right? That's just not something that mathematicians talk about normally. And if they do, they don't tend to agree about what the right definition is of a derivative at a function type, because there are multiple competing definitions that diverge. Okay, now how do you prove that? Well, the correctness proof goes via a standard logical relations argument that we phrased in a categorical way to make it very simple. But I'm going to skip that part, but I'll include it in the slide so you can look at it afterwards if you're interested. But the important part is the proof is fully compositional in the same way that the definitions are compositional. And it again makes use of this universal property of the syntax. So a nice result of that is if we extend our language with a new primitive operation or a new construct like, I don't know, coproducts, then our old proofs remain true. And all we need to do is add one more case to the logical relations proof, just check that case, and then the whole induction goes through. So the correctness proof is as compositional as the definitions of automatic differentiation are, and therefore it's very nicely extensible. Okay, I'm going to skip over this part about the logical relations proof. And I'll say a little bit about implementation challenges, because yeah, I was really practically motivated in this work, even though you might not be able to tell that from all this category theory. My hope is to still connect it to practical, yeah, a highly performant implementation, ideally, in the end. Okay, so something that we care about in our group is doing automatic differentiation on purely functional array processing languages that make use of yeah, data parallel arrays. And in particular, in the research group where I work, Gabriele Keller and Trevor McDonnell are developing the Accelerate library for array processing in Haskell. Another such library or language is Futark. But these are languages that have primitives for parallel array operations, like maps and folds and scans and that sort of thing. And so we've been looking, in particular, Tom Smading has been looking at how to apply this sort of homomorphic differentiation, this chat idea, to these parallel array primitives. And he's shown that you can actually differentiate a lot of these parallel primitives and express their derivatives in terms of other parallel primitives. So we get a sort of parallelism preserving derivative in most cases, at least the cases we've checked so far. And then you can extend the logical relations proof to apply to these cases. And again, the logical relations proof is compositional. So we just need to check one case for each operation that we add. Okay. And now I get to the part where we don't really know anymore. We're facing some efficiency challenges, and we have some solutions for them, but I'd like to be transparent about yeah, what challenges still are. Yeah, you can notice that because chat, if you don't make use of dual numbers, does this sort of split in the derivative of closures between the derivative with respect to the context variables and the arguments, you naturally end up duplicating some work in the derivative of a function body. And that's something that's yeah, really pretty annoying for efficiency. But we don't see an obvious way out of it yet, because it's sort of what the category theory dictates. The most obvious way out of it that we found that does seem to work is, well, you can just defunctionalize your program first, and then express your function types in terms of co-products and products, and those derivatives are very efficient. Or you can do a sort of closure conversion first to make sure that there are never any context variables that are captured by a function, and we can yeah, we lose this split and we don't need to duplicate the work. But it feels a little bit dissatisfactory that we need to defunctionalize or closure convert before differentiating a higher order program if we want to be efficient. Then another point of inefficiency is that reverse derivatives of projections and indexing into arrays give rise of big one-hot vectors. And that's a problem that we don't have in imperative approaches to automatic differentiation, and it seems to sort of come up in every purely functional approach to automatic differentiation that I know of. And the way that everyone always deals with this is like you work with a sparse vector representation, or you work with some representation that looks functional from the outside, but secretly does destructive imperative updates internally. And it seems like other approaches can solve this problem that way, and we're also working on a solution like that. And in this case, I'd like to note that this is a problem that every functional approach to automatic differentiation that I know of faces. So yeah, it seems to just be inherent to trying to be functional rather than imperative. But hopefully there are solutions like sparse vectors or imperative updates under the hood. Then thirdly, working with dual numbers AD gives rise to a lot of arrays of structs. And to make that efficient, what people have done and what you should do is do array of structs to structs of array conversion under the hood. And that's what we do. But that is important to make dual numbers forward AD efficient. And then finally, we often only want to differentiate with respect to certain variables, not others in our program. And we can achieve that by forcefully setting certain cotangent types that we don't care about to be equal to the unit type. And then we have nothing to propagate forwards or backwards. Okay, so these are the efficiency challenges. Then some other practical implementation challenges. Right, so you've seen that we are generating dependent types for the types of cotangents in case our language has coproducts. That might be a bit annoying if we want to implement this in real world systems, because most languages don't have dependent types. And the idea is that these dependent types give us extra type safety, and they make the semantics of the algorithm a bit nicer, and they make the correctness proofs a bit nicer. But we can also just erase these dependent types, erase all the type dependency, and keep the programs the same, and run them with in a less type safe way. So one way of doing that is, I guess, translating these case distinctions on types that we get from coproducts into an ordinary coproduct. And we keep all the programs the same. And whenever the type dependency is broken, we just throw some runtime errors. And that seems to work fine. We've implemented that. But what you get then is that the macro, or the code transformation no longer preserves the eta law for the coproduct. And that's not much of a problem, but it just makes the semantics less pretty. Okay, so that's what our implementation currently does. And then our macro or our code transformations also generated some linear types. And you might also think, well, we don't have those in Haskell either, or in other functional languages. And it turns out that all the linear types we can implement as ordinary abstract data types. So for example, the co-power of sigma with tau, we can implement as a list of pairs internally that we wrap in an abstract type. And by only exposing certain, only letting the programmer make use of the type in certain ways, we make sure that the order of elements in the list cannot be observed and that certain linearity properties are respected. So effectively, by taking this abstract type, we're taking a sort of quotient of the type semantically. Okay, then we needed a power type. Well, powers we can implement as ordinary function types in our implementation. That's fine. We don't need to use an abstract type even. Everything can be exposed. Then we had linear function types. Well, in this case, what we're really doing is we're working with a subtype of an ordinary function type. And again, we can work with an abstract type that makes sure that we can only ever build functions that respect linearity in this type. And we get the extra safety of linear types, but under the hood, our code is just going to use regular function types, right? And finally, the linear type of n-dimensional real arrays, we can just use regular n-dimensional real arrays for, because we can define the addition and zero at all types using induction. Okay. I had some slides here about how dual numbers AD precisely relates to non-dual numbers AD, but I'm going to skip those and just conclude, I think. Okay, so I'd like to zoom out a little bit more. So what's this about? What have we been doing? To which extent have we been doing automatic differentiation? Well, in many ways, what I've been talking about is much more general than automatic differentiation, right? It's about having certain structure preserving functors on the syntax of a programming language, either from the language to itself, to another Cartesian language, in the case of dual numbers AD, or into one of these sigma types of a language that has both Cartesian types and linear types. And to construct such a homomorphic functor, all we need to do is we need to associate some data with each primitive type, so floats and integers, and that sort of thing. We need to say what we're, how we're interpreting that. And we need to give a recipe for transforming that data under each primitive operation. So sine, cosine, exponential, whatever we've included. And then we get a unique code transformation that's homomorphic out of that. And presumably, if it implements some semantic notion, we can prove that the code transformation is correct for all programs using logical relations. Well, add some other examples of things you can do that aren't regular differentiation using the same framework. Yeah, if you want to look at them, they're in the slides. But I'd like to end here and give time, give like 4 minutes for questions, I guess 5 minutes. I have some references here to read up on regular chat or dual numbers chat. And yeah, there's a comic here because it sounds like we've done something very impressive here and redefined the differentiation, but ultimately it's still regular differentiation, right? People have been studying this for centuries, so there isn't much new under the sun, but the presentation is a bit different.
Okay, let's thank Matthijs. Any questions from the room? I don't see questions on the chat. Yep.
Hi, thank you so much for the very interesting talk. I have a kind of basic question. So you said everything's kind of simple if you use dual numbers. Yeah. What was the reason again to not just use dual numbers all the time for everything?
Well, for forward mode AD, I would always use dual numbers. And for reverse AD, it's not so clear to me that the dual numbers approach works so well, because the problem is sort of you need to, I don't know if I can find this slide, but as far as I can tell, this also came up in Michele Pagani's talk, you need to have a certain non-standard operational semantics for dual numbers reverse AD for it to be efficient. So you need to, where is it? Well, you need this linear factoring rule, right? This rule here to make it efficient. So that means you need to write a custom interpreter. And we want to do as much at the compile time as possible and not rely on a custom interpreter, but just rely on standard compiler tool chains. And that does work for regular, AD in reverse or without dual numbers. Let's see. I see that there's another question in the chat from Alex Liu. He's asking, in a Haskell or Camel implementation of higher order AD, assuming you don't do the defunctionalization or closure conversion trick you mentioned, could you spell out what the types look like for derivatives with respect to closed over context variables? Yes, I can. We have a Haskell implementation that you can look at. It's linked here at the end of the talk. Let's see. Well, there's a link on the last slide to our Haskell implementation that Tom Smading made, so you can look at precisely what the derivatives look like. But basically, a function type ends up getting, in reverse, ends up getting these types of derivatives associated with it. So the types of primals associated with a function type is a function that produces both a return value and a derivative with respect to its function argument. It's a linear function. And the cotangent type associated with a function is this copower, which we implemented as just a list of pairs, right? So, and basically what the list of pairs stores is, all the arguments that the function was evaluated on, so the primals, together with the adjoint contribution, so together with the cotangent contribution that needs to be propagated back to the context variables for that function input. I don't know if that makes sense, but you get this separation between the derivative with respect to the function arguments and with respect to the context variables.
We have another question from the room.
Yeah.
Yes, thank you for the talk. I'm wondering if you could perform your categorical construct on top on a differential category in the sense of blood, coquette, and silly, perhaps with additional assumptions such as categorical Cartesian closeness or perhaps more.
Yeah, that's a good question. I don't really know yet. I need to look more at the relation with differential categories, but my understanding was that differential categories are mostly related to forward AD. And now recently, there are also these reverse differential categories that were related to reverse AD. And yeah, I'm not sure if they have a higher order version of that either, but I suspect, yeah, no, I don't know what the relationship is precisely. But my impression was that the sort of differential category world was more focused on an internalized notion of differentiation, so where it's an operation in your language. Well, here we're looking at differentiation as a program transformation, so as a meta operation on the language, but this is speculation. I don't know the relationship.
So I see there's more questions in the chat, but we have a very short break now. So is that okay?
So you're proposing to skip the question in the chat?
Yeah. So let's just continue on the chat if you're online, and we can
we'll
catch up later. But let's just wrap it up here. Okay. Let's thank Matthijs again.
Thanks.